And the first presentation will be held by Hans-Günter Krull. He works for the Deutsche Edelstahlwerke, and he will show us something about new steels for additive manufacturing. And even if steel is a really old material, I mean, it is developed since hundreds of years. There are still new developments, still great developments, and at the moment, I think great new topic are additive manufacturing, and there we now will get some solutions for this technology.
Thank you for your introduction, and welcome to my talk about new steels for additive manufacturing. As already mentioned, steel itself is not new, but our company is at least 165 years old. But additive manufacturing is a new technology, and therefore we have to adapt our steels for this new manufacturing technology. It's not a work of myself. I have also introduced a few colleagues, Mr. Moore, Ms. Richard, and Mr. van Soest. Did also a lot of work on this talk. I will shortly give an introduction about how do we do steel design for additive manufacturing. Then I will present 4 new steels, and I will show you a few demonstrators and give you a short summary about the new steels. How do we design new steels? We start with wish list. We have a lot of engineers here, and I think most of them have at least one semester material science, and one common steel is a quenched and tempered steel, 24 chromium 4. Another one is also quenched and tempered steel. This is tool steel. It's an SIA designation H13. The European designation is 2444. Steel has some very interesting properties. It has a high temperature structure. It's a very dense structure, but soft. We call it austenite. It's a face-centered structure. And it has also a low temperature structure. And this heat treatment and quench and tempering process is a very nice property of this of steel, because you can adjust the mechanical properties by the heat treatment. You can adjust toughness, strength, hardness to your needs. This is a very nice property, but it caused some difficulties, as shown later. We can also do a so-called chemical treatment. We can carburize, we can increase the hardness of the outer shell of the material. You can build gears or bearings with this procedure. One of the steel is a 16 Mancro 5. It's I think always used if you have a car. It's produced in mass. We are here at the LightCon, so one point on the wish list is high strength for a lighter design. On the other side, we also talk about economics. That means we need a high productivity, even in additive manufacturing. I think we are not at the end of this process to develop a higher productivity. Then we want lower dependency of the part quality on the process parameters. If we change something, you get a new batch of powder. You don't want to start with a new process to optimize your process parameters. You take it from a data sheet of your printer deliverer or powder deliverer, and then it should work. And it should work completely independent of your printer. If you buy an EOS or another printer, it doesn't matter. You should have nearly the same process parameters or nearly the similar setup. It's not new. But it's also on the wish list, we need a low amount of conflict minerals. Actually, it's mostly nickel, but if you think on the common grade for additive manufacturing, it's the 2709. It's not only alloyed with nickel, it has also up to 10% cobalt. So starting the design of new materials or new steels for additive manufacturing, we are working with a very simple model. This is the measured elongation over the temperature, and this is valid if you have a process of rapid heating and rapid cooling, what is standard for additive manufacturing, if you produce your part layer by layer. You start with high temperature because you heated a small spot. You have a big amount of processed material. You cool very fast, and then you have a phase transition at low temperature. Normally, this is a martensite. And in this case, you have an slightly abnormal behavior of this material. You cool it down, and it increases in size. That's typical for steel, and it's caused by this phase transition from the high temperature structure to the low temperature structure. And this causes some internal stresses if we work with a model of two layers. The cold one is still the martensite, and the upper layer is transforming from austenite to martensite. Martensite can be very hard, and you produce stresses in the lower layer. Then if you heat it up very fast, you have similar structure, no phase transition, but the upper layer wants to elongate, the lower layer remains cold, and you also produce thermal stress in the lower layer. This can produce cracks. The positive point of the austenite is very soft, so by micro deformation you can reduce the stress in the layer. If you have a hard phase like martensite, the stress increases and you produce cracks. At the very high temperature, you have a reverse transformation from the low temperature phase to the high temperature phase, and this causes also internal stresses, but you are in the high temperature range, that means the material is rather soft, and you also produce additional austenite, it's also soft, so the risk of cracks in this case is rather low. So what are the right materials? Actually, we use an austenite grade, 360L. It's a pure austenite even at low temperature, and it has a low carbon content, so it has a good weldability. So this works for the case 1. It's a very good steel. The other one is a maraging steel, the 2709. It has a low carbon content, good weldability therefore, and in this case the martensite is soft because there's actually no carbon in this phase, so carbon hardens the martensite. So the stress in case 2 is limited for this 2709, so this is a good grade for additive manufacturing. So on this model, we are looking now for new grades which better fits to the needs as mentioned before. And that's for later reading. We start with high-strength austenitic steels. In this case, we have these 316Ls. Here's the analysis. The austenite is stabilized by nickel. It has a high amount of nickel. How to avoid nickel in this case? We move from nickel to manganese. It's also an austenite stabilizer. And we want to increase the strength, and therefore we increased the amount of carbon and nitrogen. Actually, the 316L has a low carbon and nitrogen content. And this causes, due to the structure of austenite, it is very soft. We call the 316L, it's a steel without properties. It's even not corroding. With this alloying with carbon and nitrogen, we avoid the formation of the martensite. We have stabilized the austenite. So in this model, we stick on the blue line for the complete building of the component. Here are the mechanical properties. The red line is the new grade HSL. We increased the yield strength, what's important for construction, nearly by a factor of 2, and tensile strength the same. For the higher strengths, you have to pay for less elongation or ductility, but the steel is still, due to the austenitic structure, very ductile, and you have a high toughness. If we compare the two grades, the HSA is nickel without nickel. It has a higher strength. The preen number is something like the corrosion resistance. It's a chromium equivalent. And the big advantage of the 316L, everybody who delivers printers has process parameters for this grade. And the HSL can be processed with the same process parameters as the 316L. You change nothing, you can print it with the same parameters, just change the powder. That was the easy task. Now it becomes slightly more difficult. We use a bainetics grade. That's, I think, for most of you, hopefully not heavy metal. This is a CCT diagram. It's a continuous cooling diagram, as mentioned. We have a high temperature phase, we have a low temperature phase. And the low temperature phase, the properties depends on the cooling rate. So if we cool very fast, we reach the martensite. If we cool very slow, we achieve a structure of pearlite and soft martensite, and we have a structure in between, that's the bainite. In the last decades, a lot of bainitic steels was developed due to the fact we try to avoid to save energy and carbon CO2 by avoiding a heat treatment. So you quench, that's the first heat treatment, and then you have to temper, that's the second heat treatment. And the idea of the bainitic steels is you have to heat up, deform, you have to do it anyway, forge, and then you cool down and and do nothing and cool with the right cooling rate, and you get a bainitic structure. And bainite looks very similar to martensite and has similar, nearly similar properties as a quenched and tempered martensite. And then you have to adjust, but to increase the range for the bainite transformation, you have to play with the chemical analysis, and this is done in this case with carbon. And to improve or to move to the ferrite pearlite reaction to longer times, you have to add molybdenum. And if you reduce carbon, you have a softer structure than a hard martensite. Here's the comparison of this development. We have a very broad range of cooling phases, cooling rates to form completely bainite. The green lines is the same CCT diagram for 24 chromium 4, and we claim we have the longest nose in the steel industry regarding the bainite transformation, because this looks like a nose. In this point, I claimed the idea is to improve the additive manufacturing process by a steel with a austenite martensite or bainite transformation to have a lower hardness. You compare the blue line, that's a new steel, with the standard tool steel, in this case a 2344, and you see over the complete temperature range you have a lower hardness, and this should improve the additive manufacturing without cracks, because you have a lower hardness and you allow some kind of micro deformation, and you will reduce the risk. Here are the mechanical properties of our grade. We call it now Bainidur AM for additive manufacturing. There's a material number, and you get very good mechanical properties. You reach yield strengths above 1000 MPa, and if you look in your car, it's far above the steels you get today. And in the as-built structure, you get an CHARPV impact toughness above 80 joules. It's even more than you have actually in your cars. So you can use this material in the as-built condition. You can do heat treatment. You can use this material also without any heat treatment. So heat treatment, you get the same results, nearly the same results as if you use bulk material. And this leads me to the next picture. What is the special use of this grade? If you start from a bainitic phase, you have an engineering steel. You can do everything on testing. You can do your chemical treatment. You can build your prototypes. If you start with mass production, you move from additive manufacturing to standard bars and forging, and have an efficient and cost-efficient process for large volumes. And then if at the end of the lifetime, you can move back to the replacement of spare parts without change of the drawing. That's an obstacle for introducing this material in the automotive industry if you have to change the drawings. The next one is the tool steel, and the design is simply developed by looking in the brochures and looking for a martensite start temperature. A lot of available machines have a preheating temperature up to 200 degrees. So we are looking for martensite material with a martensite start temperature below 200, and this is a cold work tool steel with a high amount of carbon. And so you never reach the phase transition. You stick in the austenitic regime, and this is a very easy to print material. You can use preheating temperature of 200 degrees centigrade. In the as-built condition, you get a very fine structure, and you can you can use it with as-built with a preheating of 200 degrees Celsius. You can use it even without. It's possible, astonishing, but you get a rather ugly structure. It's a mixed structure of martensite and retained austenite, and then you have to do a heat treatment. It's a view in the future. We changed the standard grade 2344. It's not very easy to manufacture in additive manufacturing. You have to have very high preheating temperatures, and we try to decrease the martensite start temperature without losing the other properties you need for this steel, or which the end user knows. Also, in CCT diagram, very simple. You just have an austenite regime and you have only martensite, so you have to adapt the heat treatment. Very similar properties. It is processable with a temperature around less than 300 degrees, but we did not reach our aim of less than 200, so we still have to work on this grade, so it's not finished. So we'll show a few parts. The first one is a part of a hydraulic block, It's done with a layer size of 120 microns. Normally they use 30 with 40. It's very efficient, and you can do some kind of high-speed printing with this grade. That's a cutting plate from this corridor grade, and we are just testing in field a mold for plastic application. So if I summarize this, we have 3 steels. At least high strength austenite with no nickel, an all-purpose steel 2980, one grade for the complete life cycle. 2842, you can use it for wear resistance for bearings, and in development we are in a good way. A tool steel with an preheating temperature less than 200 but above 200 degrees Celsius. Questions?
Thank you, Mr. Krull, for this presentation about the new materials for additive manufacturing. Are there any questions? If so, please use the microphone at the left-hand or right-hand side. If no, I have one question. Even if you print a part and it's nearly the shape you need at the end, you still have often a machining after this printing. And of course, you can nearly machine everything, but how are your materials in the field of machining? Are they easy to machine, or are they really hard?
Depends on one point is also you can slightly add sulfur. Sulfur had 2 beneficial effects. On the one side, you improve the machinability. On the other side, you decrease the surface tension of the liquid, and you improve the yield of the powder production. So sulfur is one argument. The other one, okay, you can do heat treatment, but you have to adapt your tempering procedure, because these steel grades are not useful if you make a normal soft annealing. This will not work, because for the magnitude you always reach the magnetic state. For the modified, you always get the hard martensite. So you have a high temperature annealing below the phase transformation back in austenite.
Okay, thanks. Then, if there's still no question from the audience, I have one more, of course, costs. Compared with other powders or materials, are you on the same level, or?
Depends on the grade. The HSA use manganese is cheaper than nickel, and you don't have the volatility. Carbon is more or less for free. So this is nearly this. It should be cheaper than this 316L. Bainy Duo has a problem; it's lower load, so we have a lower yield for the powder production. So we have at least the same level as for the 2709, and the high carbon grade should be cheaper.
Okay, perfect. So then, are there any other questions from the audience? If not, then thank you for the presentation.
Thank you.